Welcome to the Introduction to Probability Theory and Statistics course. We are in topic 12, analysis of correlation and regression. This is lecture 2. In the lecture 1 we have discussed about the analysis of correlation, and this lecture we are going to discuss about the analysis of regression, and in the third lecture we are going for discussing logistic regression. As I said earlier, regression analysis is concerned with the problem of predicting a variable called a dependent variable on the basis of information provided by certain other variables called independent variables. So, basically this is concerning with the problem of predicting. So, now we will move into regression analysis. First, let us start with the simple linear regression. Y is a dependent variable, x I is a independent variables. And the quantities beta naught and beta 1 intercept and the slope of the regression respectively, which are unknown parameters. Later we are going to estimate these parameters beta naught, beta 1. After that we are going for testing of hypothesis regarding the parameters also with the some known value. We are going for discussing the statement related to the unknown parameters beta naught and beta 1 also later. And epsilon is the random variable. We always make the assumption the expected epsilon i's are going to be 0. When you take a expectation on equation 6.13, you will get beta naught plus beta 1 times xi. So, the expectation of yi, expectation of y is a function of x, and it is called a population regression function. And the way we have written yi in terms of xi's, this is called the simple linear regression. So, one can write expectation of yi given xi, that is equal to beta naught plus beta 1 times xi with the assuming knowledge of xi's. You can write it as a conditional expectation of yi given xi, that is equal to beta naught plus beta 1 times xi. So, the random variable y I is called a response or dependent variable, whereas x i's are called a predictor or independent variable. The word regression is connection with the conditional expectations, that is very important. That is the regression of y on x, that is same as expectation of y given x. So, this part conditional expectation of one random variable given other random variable, that we have discussed in probability part. That is same as regression of y on x. So, we are connecting what we have learned it conditional expectation of y given x takes the value small x, that is same as, or that is called regression of y on x. That is basically in statistics to signify a relationship between the variables. When we refer to a linear regression, we mean that the conditional expectation of y given x is a linear function of x. Whenever this conditional expectation is a linear function of x, we call the corresponding regression is a linear regression. Fine. And the equation 6.15 concludes that the regression is linear whenever xi is fixed and known, and it is a realization of the observable random variable xi. Fine. If you assume that the pair xi and ya has a bivariate normal distribution, then it immediately follows that regression of y on x is linear. So, the last observation is last note is very important. If you assume xi and yi has the bivariate normal distribution, then based on the theory which you have studied, when xi is normal distribution, ya is normal distribution, and together is a two dimensional bivariate normal distribution, then if you compute the conditional expectation of y on x, that is always a linear function in x. Therefore, you can conclude regression of y on x is always linear. Now, we are coming into the point whenever the beta naught and beta 1 are unknown, how to estimate. You can define the line y is equal to c plus dx, and then you can use the least square method. From there you can able to estimate the beta naught and beta 1. So, first you create the residual sum of squares, we call it as RSS, residual sum of squares, that is difference between yi with the c plus d of x i's the whole square, and the least square estimates of beta naught and beta 1 are defined to be the value of a and b, such that the line a plus bx minimize the residual sum of squares. That means the least squares estimates a and b satisfies minimum of c comma d with the summation, that is same as the summation of yi minus a plus b x i's the whole square. Simple calculations yields the estimates of beta naught and beta 1, that is denoted by a and b respectively. The way I have written a plus b, that a is nothing but the beta naught estimate, beta naught cap, and b is nothing but beta 1 cap. Therefore, we started with beta naught plus beta 1 x. So, here we are estimating the beta naught and beta 1, that is nothing but a and b, that is same as beta naught is equal to sample mean of y minus b times sample mean of x, and the beta 1 cap, that is same as basically the b, that is same as s x y divided by s x x. So, this s x x, s x y, those variables are already defined earlier. In the analysis of correlation, we have explained this s x x and s x x. So, using the same definition, one can get the beta 1 cap, that is same as b. That b can substitute in the beta naught cap, then get the estimate of beta naught cap, that is same as e. Already we said that x is the predictor variable, then we say y is the response variable. Then we can think of predicting y from x. Then the vertical distance measures the residual sum of squares is reasonable. Let us see the simple example. We have a data for x and y with the size n is equal to 10 respectively. It is expected that y is linearly related to x. Determine the least square regression line for expectation of y on the basis of 10 observations. Based on the data, you can get the sample mean of x, sample mean of y. Then you can get SXY, SXX. Then you can get the estimates, that is beta naught cap and beta 1 cap. Therefore, the estimated regression line is y is equal to beta naught cap plus beta 1 cap x. So, we get the final the estimated linear regression line y is equal to beta naught cap plus beta 1 cap, that we got it. The same relation which we have explained in the previous lecture, one example. Find the linear regression line. So, the same exercise can be done for that problem to get that answer. Now, we discuss a multiple regression equation. In many situations, there is a simple response variable y, also called the dependent variable, which depends on the value of a set of input called independent variables x1, x2 and so on till xr. That means, we have a one dependent variable y, whereas r independent variables. The simplest type of relationship between the dependent variable y and the input variables x1, x2, xr, that is a linear relationship. For some constants beta naught, beta 1 and so on beta r, you can frame the linear equation relationship, that is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on plus beta r xr. In this we will have a error term also. We can include the error term, that is basically epsilon, that is called a random error. It is a random variable with the mean 0. We can call the equation 6.16, that is a linear regression equation. Y is a dependent variable, all the xi's or xi values are the input variable, they are independent variables, and the coefficients beta naught, beta 1, so on beta r are to be estimated from a set of data. Again we are coming back to simple linear regression with one independent variable. Therefore, y is equal to beta naught plus beta 1 x epsilon, and how one can estimate beta 1, that is beta 1 cap, that I have written. That is basically what we have written earlier, I have just elaborated in a expanded way. And here we are making a one more assumption, the random errors psi a is having a mean 0 and the variance sigma square. Therefore, if you assume y a is a response corresponding to the input variable xi, then y a is you have n data are independent, and each y a is also normal distributed with the mean beta naught plus beta 1 xi and the variance sigma square. It is possible to find the mean for estimate of beta 1. The way I have given the expression in the earlier slide, you have a beta 1 cap. This is also a estimator. This is also a statistics, and you can find the expectation of this estimator. Only thing is you can keep instead of small letters you can keep it in the form of if I go for expectation of beta 1 cap, then I will treat x bar as a random variable. Therefore, I am computing what is the expectation of the whole quantity, whereas the value of no, I am saying here when you treat this as a random variable value, if it is a value then it is a small x bar. If you consider this as the statistic, then only it makes sense to find the expectation. Summation of xi minus x bar that is equal to 0. Yeah. So, here if you see it the beta 1 cap is the estimates of beta 1. So, if you consider as a small x bar then it is a value. If you consider small x bar in the summation in the numerator and the denominator also you have a x bar square, that means if you keep the small letters, that means the value of the estimates beta 1, that is denoted by beta 1 cap. Suppose I replace this with the capital letters, that means a capital Xi minus capital X bar multiplied by capital Yi divided by summation capital Xi square minus n times capital X bar square, that means this is going to be a estimator. Fine. So, once it is a estimator, it is possible to find the mean for estimator. So, if you find the mean for estimator, that is going to be a value that is written in the right hand side of equation 6.20. But that is called the estimates value, that is not the estimator. So, we never write estimates and estimator in the different form. If it is a small letter, that is estimates, if it is a capital letter, it is estimator. So, once I write a small xi, that is a value. When I write replaced by capital Xi, that means it is a random variable takes a value small xi. So, once I create the estimates, if I replace small letters by capital letter, that becomes a random variable. Each one is a random variable. Capital Xi is a random variable, capital Ya is a random variable. Forget about the dependency between Ya and Xi, that is a different. Connection between Ya and Xi is a different story. You just think Xi is the data and capital Xi is the random variable. So, we are finding the mean keeping capital letter in the mind, not with the small letters. If it is a small letters, then it is a values. Okay. So, now we are discussing the mean for the estimator beta 1 cap. In the previous slide we have estimates. Please remember, in the previous slide we have a value, that is a estimates of beta 1, that is beta 1 cap. When we are computing mean for beta 1 cap, that means we are taking estimator beta 1 cap, finding the mean for the estimator. If you compute, you will get the value of the mean of beta 1 cap, that is going to be in the right hand side 6.20. And you can substitute expectation of Ya is equal to beta naught plus beta 1 xi, and also there is a small mistake here, it is a summation xi minus x bar bracket, that is equal to 0. It is obvious result, summation of xi minus x bar within the bracket, that is equal to 0. Using that we can able to get expectation of beta 1 cap that is same as beta 1. That means the expectation of a estimator is going to be the same variable, that is beta 1. Therefore, you can conclude beta 1 cap or estimator of beta 1, that is a unbiased estimator, that is a unbiased estimator of beta 1. You can compute the variance of the estimator beta 1 cap also. Use the same logic, you find out the variance for the right hand side what we have given in the previous equation, and since the denominator is a constant, therefore, it becomes a square, and you identify the variance of the numerator, then you can simplify and you can get the result. So, using variance of y a is equal to sigma square, you can able to get the variance of beta 1 cap. So, basically first we are finding the estimator of beta naught and beta 1, then later we are finding the expectation of estimator beta 1, that going to be the value of same beta 1. Therefore, we are concluding the beta 1 is the unbiased estimator, beta 1 cap is the unbiased estimator. Then we are finding the variance of beta 1 cap also. Now, we are coming to the expectation of a beta naught cap. So, using variance of y a is equal to sigma square, we will get a variance of beta 1 cap, that is equal to sigma square divided by this result, because there is a correction in it, this is instead of alpha square it is a sigma square divided by the denominator. Now, we are coming into the estimator of beta naught, we are simplifying that, and we can feel it the beta naught cap can be expressed as a linear combination of independent normal random variable y i's. Therefore, that is also going to be normal distributed. So, using that concept you can able to find expectation of the estimator beta naught. If you simplify, you will get the beta naught. So, that concludes the estimator beta naught also unbiased. That means you will have a both beta naught cap as well as beta 1 cap, both are unbiased estimators. Once we concluded the beta naught cap is also a unbiased estimator, we are finding what is the variance of beta naught cap. Earlier we have found what is the variance of beta 1 cap. The similar exercise we are doing for variance of beta naught cap also. So, now one can compute what is the residual sum of squares, that is nothing but in the right hand side I have written in the equation 6.24, that can be utilized to estimate the unknown error variance sigma square. Once you have a residual sum of squares divided by sigma square, that is going to have a chi-square distribution with n minus 1 with n minus 2 degrees of freedom. The reason of n minus 2 degrees of freedom, because you are using sample mean of x as well as the sample mean of y. Therefore, the number of independent informations are going to be n minus 2. Once you conclude residual sum of squares divided by sigma square has the chi-square distribution with the n minus 2 degrees of freedom, using the properties of chi-square distribution, you can say expectation of residual sum of squares divided by sigma square, that is going to be n minus 2, or one can say expectation of residual sum of squares divided by n minus 2, that is going to be sigma square. That means, whenever the variance sigma square is unknown, whenever variance sigma square is unknown, you can estimate the unknown parameter sigma square by using residual sum of squares divided by n minus 2. Yeah, that is what we are saying. The estimator of sigma square, that is going to be residual sum of squares divided by n minus 2. Just now we have concluded the expectation of estimator of sigma square is same as sigma square. Therefore, this is a unbiased estimator. Further, you can show the residual sum of squares is independent of a pair beta naught cap and beta 1 cap. It is similar to what we have proved earlier, the sample mean and the sample variance are independent. When yi's are normal distributed random variable, the least square estimators are also minimum likelihood estimators. Oh, sorry. When yi's are the normal distributed random variable, the least square estimators are also maximum likelihood estimators. Consequently, the maximum likelihood estimators of beta naught and beta 1, precisely the value of beta naught and beta 1 that minimize the summation of yi minus beta naught minus beta 1 xi whole square. That is, they are least square estimators. So, this is the observation from the estimators what we have discussed till now. So, now we discuss one simple example, that is a parameter estimation under unbiased estimator method. So, in this example what we are going to conclude, the maximum likelihood estimators of beta naught and beta 1 are the same as those obtained from ordinary least square, that we denoted as OLS. In this example, we are going to prove the maximum likelihood estimators of beta naught and beta 1 are going to be the same as those obtained from ordinary least square. So, let us assume that there are m sample points, each represented by xi comma yi. It is easy to show that the regression model can be transformed into theta transpose xi plus epsilon I, where theta is the column vector containing alpha and beta. This can be done by transforming the vector of independent variables appropriately. Now, the likelihood function is given by in the form of a product of probability density functions. If it is a continuous type, if it is a discrete type random variable, then it is a probability mass function in the product form. Since the results are in the form of exponentials, you take a logarithm of likelihood function. So, that is equation number 6.27. The first term in the above equation is independent of theta. Thus, when we differentiate a logarithm of likelihood function with respect to theta, only the second term comes into the picture. The first term does not have a theta, it is independent of theta, whereas the second term is a function of theta. Since we want to maximize the log likelihood function, we are minimizing the term which is in the second term, that is yi minus theta transpose xi whole square divided by 2 sigma square, which is same as the ordinary least square. Hence, we will get the same estimates of the regression coefficients, that is beta naught and beta 1. So, in this example we are concluding the maximum likelihood estimators of beta naught and beta 1 are same as those obtained from the ordinary least square. Now, we are coming into hypothesis testing regarding the regression parameters. Let us start with the simple linear regression model. Y as a dependent variable, x is the independent variable, and the beta naught and beta 1 are the regression parameters. We start with the null hypothesis. The beta 1 takes a value 0. So, the alternate hypothesis is beta 1 is not equal to 0. The test statistics is going to be beta 1 cap minus beta 1 divided by square root of sigma square divided by S x x, that follows standard normal distribution. And this test statistics is independent of residual sum of squares divided by sigma square, which is chi-square distribution with n minus 2 degrees of freedom. So, all these concepts we have already discussed. Now, we have a standard normal distributed random variable and we have a chi-square distributed random variable. If you recall, one of the properties which we have described during the t distribution definition and its properties, we explained this property. The standard normal distribution divided by the square root of chi-square distribution divided by their degrees of freedom, that will become a t distribution with the same degrees of freedom what you said it for the chi-square. Therefore, we get the t distribution with the n minus 2 degrees of freedom. So, we can go for having the test statistics is this t distribution, not that earlier one standard normal distribution. We are having a test statistics in the form of t distribution. So, that is going to be the test statistics. You know all the 5 steps to follow. Take a two-sided test for a given alpha or a level of significance alpha is given with the given set of observed information. You can reject the null hypothesis if the value of the test statistics is lies within the critical region. That is what we have done it. We can reject the null hypothesis if the value of the test statistics lies within the critical region. Here we have a two-sided test, therefore, your critical regions are in the both sides of the t distribution. You can find the p value also. You can find the p value. This also we have already explained how to find the p value if it is a two-sided test. So, you can identify the p value. As a remark, it may be used to test the hypothesis for any given value of beta 1, not just for beta 1 is equal to 0. In many applications, a regression coefficient is useful only if the sign of the coefficient agrees with the underlying theory of the model. Thus, it may be used for a one-sided test. We have explained it with the two-sided test. So, it can be used with the one sided test also. As a simple example, we have a test for significance of the slope component at a 5% level of significance. So, the null hypothesis is the slope component beta 1 that is equal to 0, or alternate hypothesis beta 1 is not equal to 0. So, you apply the two sided test or two tailed test, both are one and the same, and the data size is 36. So, therefore, the test statistics is going to be t distribution with 34 degrees of freedom, and then you follow all the 5 steps in the same way what I discussed earlier, then you can conclude the null hypothesis will be rejected or not. In this we are rejecting the null hypothesis. That means the slope component beta 1 is different from 0. So, we take the earlier example, that is example 6.6. That means you take the data from that example. I can go back and show what is example 6.6. Yes, you take this example data and we use the same example to consider this new example which we have going to discuss now. Yes, so we are finding the estimator of theta, estimator for sigma square. So, already we have the data. From the data you can able to compute what is the summation of I is equal to 1 to n x I minus x bar whole square. Then you can able to get beta 1 cap, and similarly you can get the, from the data you can get summation I is equal to 1 to n y I minus y bar whole square. Using that you can able to get the sigma square estimator for sigma square, that is going to be 1.30. So, we are finding the estimates of theta square. We have another example. Estimate the coefficients of the regression model. That means, you have to estimate beta naught as well as beta 1. Followed by conduct a test for a slope parameter, testing whether beta 1 is greater than or equal to 1 at 5% level of significance. So, based on the theory which I have explained, you can able to get the beta naught, beta 1 estimates. Since your null hypothesis is beta 1 greater than or equal to 1, it is a one sided test. So, you follow the similar methods what I said it earlier, find out, follow all the 5 steps, you can conclude whether to reject or not to reject the null hypothesis. So, here the conclusion is we fail to reject the null hypothesis. Now, we are discussing the confidence interval for beta 1 cap. The confidence interval estimator for beta 1, that is easily obtained from equation 6.30, that is already there. If you go back, you can find the what is 6.30 equation 6.30, you can find it from the previous slides. Using that equation, you can able to get the probability of square root of n minus 2 times s x x divided by residual sum of squares multiplied by beta 1 cap minus beta 1 lies between this t distribution with the n minus 2 degrees of freedom with the minus sign and the plus sign, that probability is going to be 1 minus alpha. This is for any alpha. We are interested to find out what is the estimator of beta 1. Therefore, the estimator of the interval estimator of beta 1. So, I think here there is a correction, I think beta 1 cap, is not it? No, it is beta 1 I am saying, this either may beta 1 needed. Yeah. So, it's a small correction. So, the probability of beta 1 lies between this interval, that is equal to 1 minus alpha. So, therefore, the confidence interval for beta 1 is the left side this quantity as well as this quantity are the confidence interval for beta 1. So, you have to read this last equation as the probability of beta 1 lies between this interval instead of beta. 100 times 1 minus alpha percentage confidence interval estimator for beta 1, that is going to be probability of this interval is going to be 1 minus alpha. So, the confidence interval is this much, that probability is 1 minus alpha. Also, as a remark, we can observe that beta 1 cap minus beta 1 divided by sigma square divided by s x x, that is going to be a standard normal distribution. Cannot be directly be applied to draw the inference about the beta 1, because it involves sigma square, which is unknown. To solve this problem, we replace sigma square by its estimator, residual sum of squares divided by n minus 2, which changes the distribution of the above statistics to the t distribution with n minus 2 degrees of freedom from the standard normal distribution. Even though this quantity is a standard normal distribution, you have to replace a sigma square by the corresponding statistics. Therefore, finally, we will end up with the t distribution instead of standard normal distribution. So, now we have another example of consider the regression equation, that is a WTI cap that is equal to minus 2.3 percentage plus 0.64 S&P 500. The question is calculate 95 percentage confidence interval on the predicted value of WTI crude oil market. Assume that the standard error of forecast is 3.67 and the forecasted value of S&P 500 excess return is 10 percentage. So, use this information to find out the 95 percentage confidence interval. So, the predicted value for WTI, that is going to be 4.1 percentage. Therefore, the 5 percentage of two-tailed critical t value with 34 degrees of freedom is 2.03. Hence, the predicted interval at the 95 percentage confidence interval is 4.1 percentage plus or minus 7.5 percentage after doing all the calculations. This range can be interpreted as given a forecasted value for S&P 500 excess return of 10 percentage, it can be 95 percentage confidence that WTI excess returns will be between minus 3.4 to 11.6 percentage. In this example, we are constructing 95 percentage confidence interval for the mean predicted value, given that the estimated value of sigma square cap, that is 0.0234, and you take the example data from the example 6.2, which is already discussed earlier. So, recall that the estimated value for the coefficients is beta 1 cap, beta naught cap as well as beta cap values are known, and x bar is 35 and S of xx is 70. So, from the least square regression line you will get y cap is minus 4.6 plus 0.2043 x, and given that x naught is 33, you can estimate a mu naught, that is mu naught cap is equal to 2.142. So, the mean weight of the cub is at 33 weeks is expected to be 2.142 kg. Now, the standard error is given by this equation 6.42, and from the t distribution table you can get the value with the 4 degrees of freedom and the probability of 0.05, that is 2.132. Therefore, finally, we will get the 95% confidence interval, that is going to be simplified into 1.9885 to 2.2955. With this, we are completing simple linear regression, multiple regression, finding the estimates of coefficients of regression line, and finally, we have done testing of hypothesis regarding the regression parameters. With this, we will complete the lecture 2 of analysis of correlation and regression topic.